Hi there everybody, this is Mr. Pope from Simpson Grammar School for Boys, and this is the second session we're going to be doing on calculus. And for this one we are going to be looking at some basic integration. Now last time we were talking about differentiation and introducing that as an operator. Today we're going to be introducing the opposite, the inverse operator, to differentiation and what that means. So, first of all, a recap. I talked about how last time we played the opposite game. So here's, let's call this an operator, and let's call this the inverse. Then if I've got an operator which is adding, then the inverse is subtracting, multiplying, the opposite is dividing. Raising something to the power is the opposite operator to the inverse operator. That is taking the nth root of that. And then, well, if I raise something to the power of n, then the opposite of that is taking log of base n of that thing. And now, if I wanted to differentiate something with respect to x, say, or it doesn't matter, I mean this x could be any variable that you're talking about, then the opposite inverse function of that will be the integral of that function with respect to x. So d of something dx, the opposite of that is this integral dx. So what's going on here? This integral sign is just a long S, and it's an S for sum. And dx, you should be a little bit familiar with after our talk last time, is it literally means a small and infinitesimally small amount or change in x. Okay, so you're probably thinking, okay, so what actually is, if I was to integrate something dx, or integrate with respect to x? Okay, so now this isn't immediately obvious, and I suggest you go away and think about this, although it's pretty easy to prove. If I've got a curve, here it is, there's my y equals my function f of x. Then if I was to find dy by dx at a point, let's say x equals p, where that's p, then dy by dx at x equals p will be the gradient of the curve at that point. So it'll be the same gradient as the tangent line to that curve. Okay, but what does the integral, so what does it mean when you take the integral? And I'm going to be traditional and say that's a. Then if I wanted to integrate f of x with respect to dx, and I was to do that between a and b, that's what this means. So I mean, technically we would write x equals a and x equals b, but we never do that because this x will always match the last dx bit in the middle. This is what we're applying our integration to. Then essentially what that's doing is between x equals a and x equals b, this is going to give us our region R. And our region R is the area under the curve bounded by the x-axis and the lines x equals a to x equals b. So if we integrate a function, okay, between two limits, these things are called limits. This is your actual integral. This bit some people refer to as the differential. And essentially, once we perform this process, the end result is called the integrand. So I'll talk about that a little bit more. But essentially, there's two types of integrals. Okay, there's two types. There's finite and there's indefinite. Okay, finite integrals have limits. So between a and b, f of x dx. And these always equal some constant that you need to find. Whereas an indefinite integral between b and a of f of x dx, we will say that will become a new function, f of x, capital F. Notice the difference between little f and capital F. We call this the integrand, and there's always going to be a constant of integration added. Constant of integration. Okay, now there's a lot to unpack here. Now let's think about why that's the case. Well, do you remember that when I differentiated, so let's remember that when I differentiated a function of x, let's say x squared plus 2x plus, say, 3, that's the same as if you differentiated the one at a time. So differentiate x squared, you bring the power down, 2, and then this is x to 1 less than the power, so it's x to the 1, plus, this is 2x to the 1, so bring the power down to plus 2, x to the 1 will become x to the 0, so that's a constant, and the constant term 3 disappeared, so we're left with 2x plus 2. Do you notice how by differentiating this quadratic, it's now become a linear term? So if I was to integrate this back, I would get a constant term. Now I can work out the 2x would become an x squared plus 2x, which would be an x squared. I can work out the 2 would become a 2x. But this plus 0 here, well, that 0 could have come from anything. I'd still get the same result if this was a 4, or if this was a 5, or this was a 16. All of these things are going to be the same. Look, if I differentiate x squared plus 2x minus 5, that's still going to be 2x plus 2. If I was going to have d by dx of x squared plus 2x minus 6,000, that's still going to be 2x plus 2. The point is, the information about what this constant term was lost. And so what we say is, there must have been always some arbitrary constant that we've yet to find. And sorry, indefinite integrals do not have limits. That's the main thing. Okay, sorry, my bad. Okay, so what does this all mean? Well, let's take a sidebar. Do you remember that when you differentiate, let's say it was k to the x to the n, this became n times k times x to the n minus 1. And do you remember what that meant? That meant you bring the power down, you bring this power down as a factor, and then you subtract 1 from the power. Now integration for polynomials, kx to the n dx, this is just going to be, you add 1, you just do the reverse. So you do the reverse, you do the opposite and in the reverse order. So if the last thing was subtracting 1 from the power, we're now going to start with adding 1 to the power. And then if the first thing we did was divide, is times by the power, then the last thing we're going to do is divide by that new power, so n plus 1, plus some constant. Okay. Now, the fundamental theorem of calculus is the integral f of x dx between a and b is just capital F of b minus capital F of a. And by the way, capital F is what happens when you integrate the function of x. So if I wanted to find the area under a curve, I'd integrate, sorry, I'm making mistakes everywhere. I'd integrate that function to find the integrand, and then I would substitute in the limits and take one away from the other. Notice how there's no plus c there. So actually, let's probably take an easy example. Okay, let's take a really simple example. Let's suppose I've got the function y equals 3. Okay, what does y equals 3 look like? Y equals 3 is just a horizontal line looking like this. And it's 3 high. It's nothing magical. And let's say we're interested in finding the area between, let's say, 2 and 4. So if I trace this up, and I trace this up, I want to find this area under the curve. And you're probably thinking, well, that's a silly question. Why? Because it's clearly a rectangle with height of 3, because the y-axis, the curve is y equals 3, so it's 3 high, and the base is 2 to 4, so it's 2 wide. So this is clearly 6 units squared. I don't need to do any calculation. Okay, well, how about we integrate and see what would have happened? So that means we're going to have to integrate between our two limits, so the upper limit first, which is 4, and the lower limit 2, because these are our x equals what limits. And then our function is 3, and then it's dx. Okay. Now for the record, 3 equals 3 lots of x to the 0. And what does our rule tell us? Our rule tells us to integrate, we add 1 to the power and divide by the new power. And this works for polynomials. So if I add 1 to the power, it's going to be 3x to the 1, which is 3x, divided by 1, and then there's plus an arbitrary constant. And now what we do is we put a little square bracket around the integral to remind ourselves we've done the integration and we're done. And we're going to put a little 4 and a 2 here to remind ourselves it needs to be evaluated between 4 and 2. Okay, now next up, to evaluate this, let's call this I for integral. Then I'm going to have bracket, bracket, minus bracket, bracket. And now looking at the fundamental theorem of calculus, we're going to sub in the top limit when x is b, and then we're going to minus the bottom limit when we sub in a. So we're going to have in here when x equals 4, and on the right hand side when x equals 2. So this is my f of 4, and I'm going to minus capital F of 2, where capital F is what's called the antiderivative, so the thing that you integrated your function to get. Okay, so what happens when we sub in 4? Well, there's only the x there, so it's going to be 3 times 4, which is 12, plus some constant. Then on the right hand side, I'm going to have 3 times 2, which is 6, plus some constant. And if you look very carefully, the plus c minus that plus c always cancels for definite integrals, i.e. integrals with limits, which this one does have. So you can usually skip this step, and a lot of the time you will. People will look at you funny if you keep putting plus c's in there. It's good practice, but you don't need it. So this integral will be 12, because that's what the first bracket evaluated to, minus the second bracket, which is 6, and this is 6 units squared. Okay, so does our answer match up? Yes, it does. By the way, what happened here? Well, do you get that by finding the antiderivative, f of 4 would have found the area up to and including 4 from 0, like so. And can you see why that area is 12? The purple stuff is 12, because it's 3 high by 4 along. And then we minus, and then, I don't know, let's dark blue. And then f of 2, oh, that's not a good colour. And f of 2 is the area from 2 backwards, like so. And can you see how if you minus the green rectangle from the purple rectangle, you'll get this desired bit that we want. Okay. Now, there's a couple of things to comment about that. One, this technique, where the power comes into it, is it doesn't matter what the curve is. It could be curvy, it could be loopy, it honestly doesn't matter. So in the case I just did with a rectangle, it seems stupid to overcomplicate things. But let's suppose I was interested in a more difficult problem. Let's say, okay, and let's make this all a little bit smaller. Let's take a more challenging example. So let's suppose I have the y equals x squared plus 2x graph. So with a little bit of factorization, this becomes x times x plus 2, which is going to cross the x-axis at x, and at minus 2, it's going to look like this. Okay, so there it is at 2, there's 0. Right, okay, so question. Let's suppose we're interested to know what is the area of this little bubble down here. Okay, we want to know what the area of that thing is, and it's not immediately obvious what it is. It's not the same shape as a semicircle, so we can't just approximate it like that. So what would integrate? Oh, this is a minus 2, by the way. So what does integration tell us it should do? Well, we should integrate between the lower bound, which is minus 2, the upper bound, which is 0, the function itself, which is x squared plus 2x, and then with respect to x. Okay. So, right. Let's deal with this. Mechanically speaking, this is relatively easy to sort out. If we call this I. Okay, x squared, you add 1 to the power, so that's cubed, and you divide by the new power 3, plus 2x squared, where you add 1 to the power, it becomes x squared. If you divide by the new power, you're going to get 2 over 2, which is just itself 1. So, and then we plus c, and then remember that this is integrated between minus 2 and 0. Okay, and then fundamental theorem of calculus time. We're going to do f of 0 minus f of minus 2. So we're going to have brackets, brackets, minus brackets, brackets. When you substitute 0 into this, you're going to get 0 cubed over 3, which is 0, plus 0 squared, which is 0, plus c. Minus, and then when you sub minus 2 in, you're going to get minus 2 cubed, which is minus 8 over 3, plus minus 2 squared, which is plus 4, and then plus c, and then again, the plus c's always cancel. So minus 8 thirds plus 4, which is 12 thirds, becomes minus 4 thirds. Positive 4 thirds. But then there's this minus here. So then we get I is negative 4 thirds. Okay, now here's the problem. What does it mean if your integral spits out a negative number? Well, we've just seen what happens when it spits out a positive number. It's when the area is above the x-axis. But when it's below the x-axis like this, you're going to get a negative result. So in actual fact, the area of this thing is just 4 thirds units squared. But if you just do the integral blindly without thinking, you're going to get a negative result. Now here comes the problem. Suppose I was interested in the total area between minus 2 and positive 2. So I had something like this. Now look what happens. If I'd have not thought about it, it would have been the same steps. So let's call this region 2. Well, what would have happened is to get region 1 and region 2, I'd have done the integral between minus 2 and 2 of x squared plus 2x dx. And that would have just been x cubed over 3 plus x squared. I won't bother with the plus c anymore. And this is between minus 2 and 2. Then what would have happened, this I2 would have been, when we sub in f of 2, which is 2 cubed over 3, which is 8 thirds, plus 2 squared, which is 4, minus f of minus 2, which we know what that is already. That's 4/3. And now look what happens. 8/3 plus 4, which is 12/3, is 20/3. But then if I minus 4/3, I get 16/3. Now, is that the right answer? Well, we've already discussed when you substitute in a limit, that essentially tells you the area of it up to and including that limit when you go from x is 0. So really, this red bit has an area of 20/3. And this 4/3 is actually being subtracted from it. So if you're not careful, you could wind up with negative areas cancelling out positive areas. And that wouldn't be a good idea. So what am I trying to say? I'm trying to say that what you can do is, and this is another fundamental like theorem of calculusy bit, suppose I wanted the integral from a to c fx dx. This is the same as the integral from a to b, an intermediate point, f of x dx, and then I can add the integral from b to c, f of x dx. So what I'm trying to say is you can break up the integral however you want to. Okay, so what we could have done here is we could have done the orange bit first, made it positive, and then we could have done the second bit. So how would this change the calculations? Well, instead of between minus 2 and 2, it could have gone from 0 to 2. So the lower limit now would be when I sub 0 in, which is 0 cubed over 3 plus 0 squared, which is 0. This now becomes 20/3. And now I can make a judgment to say that the stuff on the right is 20/3, the stuff on the left is 4/3. So when I add it together, it's 24/3. So the net area is 8 units squared. Okay, now that I've done a couple of mechanical examples of the area, I want to show you why we use this symbology. And the way I talked about calculus last time is calculus is used when things are being either made infinitesimally small or infinitely large. And you're probably wondering, okay, how is stuff being infinitely large here? Well, okay, if I wanted to find the area under this curve, what I could do is say there's a particular y value here. At this point, y equals f of x. And what I could do is I could make a rectangle like so, and make that rectangle some change in x thick. And now the area of this rectangle is going to be the height, which is f of x, and then times it by dx. And then s is just the sum. So what integrals are they're saying they're the sums of the y's times by the dx's, i.e. the areas of all the rectangles. And as dx tends to 0, imagine summing up infinitely tiny, minuscule thickness, equally spaced rectangles that completely fill up the graph. Now the skinnier the rectangles, the more you'll need of them, but the better representation the area under the graph will be. And clearly in the limit, as in not actually there but approaching to, as that limit of the thickness of the rectangles tends to 0, this will be a better and better approximation. So I don't know, maybe I'll draw a different example. Let's say I've got something like this. Here's my area. If I was to approximate the area between these two bits, these two limits, by just two rectangles, 1 and then 2, that's not particularly good because I've underestimated it here and I've overestimated it there. It might cancel out, but that's not particularly good. How could I improve this? Well, instead of dividing it into 4 bits, into 2 bits, I could divide it up into 4. So now if I divide it up into 4 rectangles, I might have a rectangle there, whoops, I might have a rectangle here, like that. I might have a rectangle there, I might have a rectangle there, like that. Now it's already starting to look a bit better. And now instead of 4, you might say, well, what about 8 then? So why did I do that? So there's, hold on, here's my 4. If I want to split it into 8, I'll just divide them all in half. So this is between A and B on the X. So clearly if I join that up, and then join that up, and then that up, and then this up, and then this up, and then this up, this up, and this is already starting to look a bit better. And my point is, if you make the thickness tend to 0, or you get skinnier and skinnier and skinnier, then this is going to be a better and better representation of the area. Now, the second half of what we're going to be talking about, or probably in the latter section, we're going to be looking at numerical methods, okay, which kind of build upon this idea. And there's various numerical methods to talk about, but the only ones I'm going to be talking about are just 2 of them. That's the Trapezium Rule and Simpson's Rule. But yeah, the key point is that the area is essentially the limit as dx tends to 0 of the sum of f of x times by that change dx. And this sigma is the Greek letter for s, it means sum. And if I was to draw it properly, you might see it in books looking like this. So it's like solid, douche, 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 a little bit there and a little bit there. And another way of writing this, and the way we normally write it, is just the integral between the 2 points a and b f of x with respect to dx, like so. Okay, that's a really important point. Okay, so integration is the reverse process of differentiation, and it turns out that it's the area under a graph. Now, there's various properties you can use with this, and one thing I want to make completely clear, this rule here, this rule, right, this is the power rule of integration. This only works with polynomials, okay? And the special case of where it doesn't work, is when we're dealing with x to the minus 1 or 1 over x is the same thing. Okay, that's really important. This power rule of integration only works with polynomials, and you can't just apply it to any polynomial. It doesn't work when you're dealing with 1 over x. Okay, so what do you mean it only works with polynomials? Well, if you want to integrate, let's say, sine of x dx, then you're out of luck. If you wanted to integrate cosine of x dx or any other trig function like tan, you're out of luck. If I wanted to integrate ln of x, that's not a polynomial, so that can go. If I wanted to integrate e to the x dx, that wouldn't be. And if I wanted to integrate something like 1 plus 1 over x squared dx, this isn't technically a polynomial. What do I mean by polynomial? Polynomial, I can write it as f of x equals some constant a0 plus some constant a1 times x plus some constant a2 of x2 plus da 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 da. And essentially, I could also include, well, essentially I can include anything of the form a constant times by x to the power n, where n belongs to the set of, yeah, real numbers is fine, but we can't let n equal to minus 1. Yeah, pretty much it. So as long as it satisfies the sequential adding of x terms, and they're x to the real numbers, then we're fine. Okay, so an integral you should be able to do is, let's say I want to integrate x cubed plus 2x to the half minus 3x squared 2/3, sorry. That's fine because they're just x to the powers plus x to the powers plus x to the powers. That's totally fine, dx. Okay, and that's really easy to do. So you add 1 to the power, so x to the 3 becomes x to the 4 over 4, plus add 1 to the power, half plus 1 is 3 halves, and then you divide by the new power. So dividing by 3 halves, same as times by 2/3, 2 times 2, that 2 times 2/3 is 4/3. And then 2/3, and then the next one, 2/3, add 1 to it is 5/3. Divide by the new power, so dividing by 5/3 times by 3/5, this becomes minus 9/5. And then we always add an arbitrary constant of integration because this is an indefinite integral. And by the way, indefinite integrals have limits as well, we just don't write them, and their limits are from x goes to negative infinity to x equals positive infinity. They're indefinite, they just go on forever. We don't actually evaluate them, it's meaningless to do so, but essentially it just means everywhere. Okay, right, a couple of applications or consequences. So a couple of consequences. So for example, if I wanted to integrate let's say f of x plus a different function of x plus, say, a different function of x dx. Let's say I've got multiple functions in there. That is the same as if I integrated one of them, plus if I integrated the second one, plus if I integrated the third one. Okay, so just like differentiation, it's a linear operator, I can separate the integrals. Okay, next up. If I have a some constant value, and this is important, of f of x dx, then this is the same as if I take the constant value out, f of x dx. Okay, so it's really important. So for example, if I had the integral of 2x squared dx, that's the same as 2 lots of the integral of x squared dx. Okay, so it doesn't. So I can take constant terms like 2 out. That's fine. Okay. There's a couple of other neat tricks you can do with integrals, and essentially one set of tricks comes down to whether a function is odd or even. And okay, to define that, it's really easy. Even functions are when if you replace x with minus x, then essentially it does nothing to the function. So an example of that would be x squared, because if you replace x with minus x, it becomes minus x all squared, and minus x times minus x is still positive squared. So that's fine. That's an even function. And now an odd function is where if I replace x with minus x, that's the same as negative f of x. So for example, x cubed is odd, because if I replace minus x in there, like that, then minus x times minus x times minus x is negative x cubed. And that's clearly minus lots of the x cubed we had to begin with. So, spoiler alert, if the power is even, it's an even function. If the power is odd, it's an odd function for polynomials. There are some trig functions that are even, like cosine of x. There are some trig functions that are odd, like sine of x. And there's some functions that are neither odd nor even. So some functions are neither so you may get that some functions just aren't odd or even. Okay, so what's the point of that? Well, if f of x is even, then f, okay, this is really important. If f of x, if the integral is being evaluated by a symmetric limits, i.e. you're going minus a to the left and positive a to the right, and you're integrating f dx, well, look what happens. Okay, what would happen here? Well, if it's even, then you're just going to have 2 lots of the integral of f of a at the end of it. or rather you're just going to have two lots of the integral between 0 and a of f of x dx. Why is that the case? Well, let's say I take a really easy one, y equals x squared. Now that's even, because I've just shown that already. And let's say I want to integrate it between minus 2 and 2. Well, so what would that give me? That would give me the area under the curve, like that. It's these bits here. Now clearly, by symmetry about the line x equals 0, then this area is the same as this one. So in actual fact, all I have to do is find this area to the right, and double it. And that's exactly what this integral was saying. And now it's even easier, because if f of x is odd, then the integral between minus a and a of f of x, if f of x is odd, well, what would happen there? Well, let's take the x cubed function, looks like this. And if I go between 2 and negative 2, then I'm going to be wanting this area here plus this area. And look what happens. Because there is rotational symmetry order 2, i.e. if you flip this 180 degrees, it's the same, then this area will cancel with this one, because areas under the x-axis are negative and areas above the x-axis are positive. So this will be really easy to sort out. Because it's symmetric, this just equals to 0. So sometimes you can save yourself a lot of bother. I mean, put it this way, if I give you some absolutely horrible thing, like the integral between minus 100 and 100 of, say, 7x to the 7 plus 14x to the 3 minus 5x plus 7 to the x to the 101 dx. Why has this trick saved you? Because 1, the limits are symmetric and every single power polynomial is an odd number. So I can just jump to the chase, and because I realise that this function is going to be rotationally symmetric about the origin by order 2, that this limit is just going to become 0. This integral is going to become 0. So that's quite interesting. Okay, so the main thing I wanted to get over to you now is how to play around with integrals. Okay, when you can take constants out, you can break things up. Why you have to add a constant of integration sometimes. Let's box this up. What is an odd and even function? How to evaluate integrals, what that means, what you have to be careful of. Where integration came from. Why do we do it? To be fair, where integration came from is a bit of a hotly regarded topic. A lot of Europeans would say Leibniz, some people would say Isaac Newton. It depends which source you read. I like to think Isaac Newton, but I probably think deep down it's probably Leibniz. And yeah, it's not particularly important. If you want to go away and research that, it's totally up to you. But as always, it's probably best if I just crack on with some questions. So, okay, so first question. If f of x is x cubed plus x squared minus x plus 15, where x can be any real number, show that x plus 3 is a factor. Okay, now some of you that have seen this already will know about the factor theorem, and that's something I'm going to be learning soon. But in actual fact, we can actually factorize this without too much fuss. So let's play a game. If it is a factor, then it must be x plus 3 times by something to get this thing up here. And let's put all my stuff in red. Okay, so let's think about it. Well, the number term is 15. There's plus 15 at the end. And I'm going to get a plus 3 times what is 15. Well, this has to end in a plus 5, or whatever it is. The highest power is x cubed, and that's going to be x times by something. Well, this has to be an x squared. Now let's think about it closer. If I were to expand this, I've considered the 3 times 5 and the x times x squared, but what about the 3 times x squared? Well, then I'd get 3x squared. But then there's also going to be an x times this term, and how many x's must be there? Well, I've got 1x squared there, but I've got a 3x squared from here, so this must be a minus 2x. And now, if I stand back and have a look to see whether that works or not, I'm going to have x times x squared, which is x cubed, x times minus 2x, which is minus 2x squared, and an x times plus 5, which is plus 5x. Then 3 times x squared is plus 3x squared, 3 times minus 2, which is minus 6x, and 3 times plus 5, which is plus 15. There's 1x cubed, so that's fine. There's minus 2x squared plus 3x squared, so there's a plus an x squared. There's a 5x minus 6x, that's minus an x, and there's plus 15. So where are we looking for? X cubed plus x squared minus x plus 15. All right, cool. So it is indeed a factor because I factorized it into a quadratic. I don't think it wants you to actually factorize it, just show that it is a factor. But just factorizing like that would be fine. Okay. The figure below shows the curve C with equation y equals f of x. Points A and B are stationary on C. Okay. So, if A and B are stationary, then that means f dashed of x, which is when you differentiate the function, so x cubed becomes 3x squared, x squared becomes plus 2x, minus x becomes minus 1, 15 differentiates to nothing. The stationary points are when f dashed of x equals to 0. So if I was to solve 3x squared plus 2x minus 1 equals to 0, does that factorize? Can I think of two numbers that add to 2 and multiply to the outside product? 3 times minus 1 is minus 3. I believe that's 3 and minus 1. So this is going to be 3x squared plus 3x minus 1x minus 1, which is 3x lots of x plus 1 minus 1 lots of x plus 1. So I'm going to get 3x minus 1 times by x plus 1 equals to 0, which means either x equals a third from this bracket or x equals minus 1 from this bracket. And it's pretty obvious from the sketch that b must be the third, x is a third, and a is minus 1. Okay, cool. Find the exact coordinates of a and b. Well, a has an x coordinate of minus 1 and a b has a y coordinate of a third. But to get the y values, I'm going to have to sub them back into the original thing at the top. Okay. So, minus 1. Minus 1 cubed is minus 1, plus minus 1 squared is 1, so they cancel. Minus minus 1 is 1. That 1 plus 15 is 16. And I sub in a third. It's a bit trickier, but we can do this mentally. A third cubed is 1 over 27. Plus a third squared is a ninth, which is 3 over 27. Minus 1/3, so that's minus 9 over 27. Plus 15. Okay, 1 plus 3 is 4. 4 minus 9 is minus 5. So it's 15 minus 5 over 27. And for the interest of saving time, that is going to be 400 over 27. Okay, so I've done that part. My answers to this is minus 116 and 1/3 400 over 27. Okay, the finite region R is bounded by the curve, the x-axis, and the straight line segment O, where O is OA, where O is the origin. Okay. Determine the value of R. Okay. So, well, I've already shown that this thing, that f of x factorizes to this. This right-hand side doesn't factorize any further. The reason I can show that is because b squared, which is minus 2, so that's minus 2 squared is 4, minus 4 lots of 1 lots of 5, well that's 4 minus 20, which is negative 16. That has no solutions. So the only solution where it crosses the x-axis is when x plus 3 is 0, So I know that this point here is x is minus 3. And now that I know how to integrate things, I know how to find this curvy section of the area. And the stuff on the right hand side, if you look at it carefully, is just a triangle. It's a base of 1 and a height of 16. So this area is 8 units squared. So all I have to do to solve this is integrate between minus 3 and minus 1 of my function, which is x cubed plus x squared minus x plus 15 dx. And then whatever that number is, I add 8, and that will be my region R. So R is 8 plus, let's integrate this. X cubed becomes x to the 4 over 4, add 1 to the power, divide by the new power. X squared becomes x cubed over 3, minus x becomes minus x squared over 2, and 15 just becomes 15x over 1, which is just 15x. This needs to be evaluated between minus 3 and minus 1. Okay, so R is going to equal 8 plus brackets, brackets, minus brackets, brackets. And this is when I substitute x is minus 1, the top one, and this is when x is minus 3. Okay, so for the top one, minus 1. So all the even powers are going to be made positives. This is going to be positive a quarter, minus a third, minus a positive, so it's minus a half, plus 15 times minus 1, which is minus 15. Minus, and then when x is minus 3. Okay, minus 3 to the 4, this is 81, so that's 81 over 4. Minus 27 over 3. Minus 3 squared is 9 over 2, plus 15 lots of minus 3, which is minus 45. Okay, let's deal with this. Well, a quarter minus 81 over 4 is 80 over 4, so minus 80 over 4, so that's minus 20 already, so gone and gone. Minus the third, minus 27 over 3, is going to be 26 over 3, I believe. So that's gone and that's gone. Minus a half minus 9 halves is minus a half plus 9 halves, which is plus 8 halves, which is plus 4. So that's gone and that's gone. Then minus 15 minus 45 is going to be plus 30. That was a 4. Okay, so what have we got here? We've got 8 plus 30 plus 4, so that's 42, minus 20 is 22, so it's going to be 22 plus 26 over 3. 22 is 66 over 3, plus 26 over 3. 60 plus 20 is 80, so it's going to be 92 over 3. Yeah, just leave it as that, 92 over 3 units squared. 90 over 3 is 30, so if you want to write it as 30 and 2/3, it's completely up to you. Okay, right, actually, going back, there is one more integration. It's quite important. To be honest, there's so many tips and techniques with integration that I'm going to forget them. That's unfortunately just the way it's going to be. But this one I think is quite important, actually. And that is what happens if the shape is a little bit more complicated. And to be fair, you could probably piece this together. But let's suppose I've got a function looking like that, where this is f of x. And let's say I've got another function looking like that. This is g of x. And let's suppose I'm interested in the area of this overlapped bit in the middle. Now, I haven't shaded all of it, but you get the idea. It's like this eye section, this eyeball section. Okay, how would you find the area of that bit? Well, let's think about that. If that top limit is b and that bottom limit is a, then if you think about it, if you do the integral between a and b of f of x dx, you will get all of this area, won't you? All of that red bit. And then what you'd need to do is subtract between a and b of g of x dx, because what would that be? That would be just this area underneath it, like so. But now here's the brilliant bit. Because the limits are the same for both of these, you can merge these together. So this is actually between a and b of f of x minus g of x. So what this is saying is that if you want to find the area between two curves, then you can subtract the top curve away from the bottom curve. And what do I mean by that? I mean, look, now if the f of x curve is in the region above, it's the top bit, isn't it? It's the top curve. It's the curve bounding it from above. If you do the curve bounded from above, which in this case is f of x, and you subtract the curve bounded from below, which in this case is g of x, this curve here, then you don't have to do separate integrals. You can do it in one go. Okay, now there's loads and loads and loads of tips and techniques, and I'll be going over them in the STEP stuff, in the UKMT stuff maybe, just as and when we go. So I'm sorry if I don't, to be honest, I'm only going to go through like some critical ones, but if it comes to mind while I'm doing this, then please, bear with, and I will be jumping backwards and forwards. Okay, so here's one you might want to try yourself. So I'm just going to get a drink, so pause the video, give it a go. Okay, so the figure above shows a cubic curve with equation y equals x cubed minus 8x squared plus 16x. The curve meets the x-axis of the origin at the point A. Show clearly that x equals 4 is at A. Okay, so let's try and factorise this, because when curves are on the x-axis, that is when y equals 0. And if I want to set this equal to 0, i.e. this whole thing equals to 0, it's really powerful, just like with quadratics, if you factorise them. Because we know that something times something equals 0 means that one of those terms must equal to 0. So the first thing I'm going to look at is every single one of these terms has x involved. So I know I can take x out, and this is going to be x times by x squared minus 8x plus 16. Okay. And now, after a little bit of thought, you can clearly see this is x times x minus 4 times by another x minus 4. Okay, so this actually becomes x times by x minus 4 all squared, which means either x is 0, which corresponds to this bit, or x minus 4 equals to 0, and if x minus 4 equals to 0, then x equals 4. And this squared thing means that it's got a 0 at 4 twice, i.e. it crosses the x-axis twice at 4. And what does that mean? Well, it means that your curve is going to do this bouncing thing. It's just going to skim it. Okay, it's just going to touch it. So yeah, the coordinate of x at A is clearly 4. Okay. The finite region R is bounded by the curve and the x-axis. Find the exact value of R. Okay, well that's pretty obvious. We've got to integrate this thing between 0 and 4 because that's our lower limit and upper limit. And yeah, we just have to integrate x cubed minus 8x squared plus 16x. Okay, that's pretty easy. We can integrate them one at a time. So this is going to be x cubed is going to be x to the 4 divided by the new power minus 8x cubed divided by the new power plus 16x squared divided by the new power is going to be x squared times by 8. This is going to be between 0 and 4. And this R value is going to be, when I sub in x equals 4 minus, and then clearly when x equals 0, all these terms disappear, right? Because 0 to the 4, 0 to the cube, 0 squared, they're all just 0. Now I sub in 4, I'm going to have 4 to the 4 divided by 4, so that's 4 cubed, which is 64, minus 8 times 4 cubed over 3, so that's 8 cubed lots of 64, I believe, and then plus 8x squared. Well, that's 2 lots of 4 cubed, isn't it? Because 8 is 2 times 4, so it's 2 times 4 times 4 squared, so that's 2 times 4 cubed. So that's 2 lots of 64. And the reason I've done that is because 2 is 6/3, and I've got this as like a multiple of 64. I've just shown you why I'm doing this out of calculator. So I've got 64 lots of 1 minus 8/3 plus 6/3. So 6/3 minus 8/3 is minus 2/3. 1 plus all that is, this whole thing is just going to become a third, isn't it? Yeah, pretty sure. So the answer is just 64 times 1/3, which is 64 over 3. So yeah, it's a relatively easy question. Causes. Is there anything else? Oh, I feel like there's something and now it's gone. No, it'll come back to me, I'm sure. Yeah. Okay, so now some questions at A level, I wouldn't say they're too difficult. I mean, integration is one of the harder topics. At A level, you're going to have some students that just struggle with the core concepts of integration. Either they don't conceptually get it, or they kind of feel that there's so many different tips and techniques that it's just beyond them. I think the analogy way of describing what's going on is with differentiation, you can just apply 2 or 3 techniques, which we're going to see, to pretty much any function of x. And differentiating things is really easy on the whole. I mean, you have to be careful, but it's straightforward. Integrating functions of x, however, not so straightforward. There's some integrals that don't exist, or we haven't figured out how to do them as a human species. Some integrals, you know, if you change one little thing, you have to completely change the technique you were going to use to solve them. The way I see it is differentiation is the easy part, which is kind of like putting a padlock on a locker. It's really easy, just snap it on, it's done. Whereas integration is kind of undoing that locking process. It's like picking locks. It's a lot harder, you need specialist tools, you need a bit of training, patience. It's not immediately obvious, and sometimes you have to keep trying. But some integrals, if you've done them millions of times, you can kind of identify what's going on. Now, there's a couple of numerical approximations for integrals I want to go over. Now, the first one, still feel there's like something I'm missing from here. It will bite me in a second. Now, when I talked about it, now you probably thought, okay, so he's saying that integration is like finding the area under a curve by breaking it up into these blocks. And if you make those blocks infinitely skinny, then it will be a good approximation, or it will be the area under the curve when those skinny blocks tend to have an infinitesimally small width. And that's technically true. However, sometimes functions are impossible to integrate. We either don't know how, or they're just difficult, or we don't want to spend so much time doing them. There could be various reasons, or sometimes we just want a rough estimate. Okay, now one of the ways of estimating is what we're going to be looking at. It's called the Trapezium Rule. Now, before I broke things up into rectangles, and now what we're going to be doing is breaking things up into trapeziums. It's pretty easy, and you'll see why the rule is what the rule is. So, same deal. Let's suppose I've got my function of x like this, and let's say I'm interested between this value a and this value b. And now, here's where it gets a little bit technical. This starting height here is y0, some initial y value. And now what I'm going to do is I'm going to imagine a width h, like so, that goes up. So it's h wide. So let's make this a bit more distinct. This width of this thing is h wide. But now I'm actually going to draw a straight line from there to there like so. And if I'd done this properly instead of being a spoon, like that, then you can see that that's even better approximation than just flatten it off and making a rectangle like that, or indeed make it a rectangle like this. Now, whether you make a rectangle like this or you make a rectangle under there, you could say it's the left-handed or right-hand Riemann sums. Riemann. I never had to pronounce that properly. I know it's not Riemann, that's not right, and it's not Riemen either, because Riemen is German for belt. I want to say it's Riemann. But anyway, probably mispronouncing it. It's okay to say Riemann, I guess. I wouldn't say Riemann, even though it looks like it probably should be said that way because it's got two N's, but the Germans don't pronounce it that way, so I wouldn't say Riemann. Riemann is fine. Riemann. Anyway, that's not the point. It's pronounced Riemann, if you want to Google it yourself. The point is, if I break the area under here into lots and lots of these trapeziums, like so, then that's also a good estimate of the area. So this point here will have a y value of y1, this point here will be of y2, next one will be y3, next one will be y4, and so on and so on, and this will be yn, the last one. So let's have a look. What would the area of the first trapezium be? Well, because the heights are the parallel lengths and h is the width, then it would be y0 plus y1 all over 2 times by h. And then if I add the next trapezium, then it would be y1 plus y2 over 2 and then times by h, and then plus, and then I carry this on, and then the last trapezium would be y of n minus 1 plus y of n all over 2 times by h. Okay, so this trapezium is this one, this trapezium is the next one, there it is, and then this trapezium, which I haven't drawn it yet, would be for the trapezium right at the back end. Essentially, you're adding up all the trapeziums, so this is a good approximation for my integral I, or where I is the integral between a and b of f of x dx. Okay, couple of points to make. Well, first of all, because they're all equally spaced, do you notice they all have h in common? And do you also see that because we're dividing by 2 each time, then I is going to be h over 2, lots of, because we can take h out of 2 as a factor. And let's think about it. I've got a y0 there, which is y0, plus, and I've got a y1 there, but I've got another y1 there. So it's going to be 2 lots of y1 plus, and then I'd have a y2 there, but then for the next trapezium, I'd have y2 plus y3 all over 2 times by h. I'd have a second y2 there. So I'd have 2 lots of y2, and so on and so on. And then this y of n minus 1 would have another one from the previous trapezium, yn minus 1, yn minus 2 over 2 times by h. And then the yn would just be on its own. So another way of writing this is I is approximately h over 2 times by the first y value plus the last y value plus 2 lots of all the y values in between. Okay, so how about we look at a previous example? This is it. This is it. This is the trapezium rule. You don't have to memorize this. It's in the formula sheet for A level. I suggest you memorize it because it's pretty easy. So let's go back up. What did we say? Well, we wanted to prove, okay, let's say I want to work out this integral again. So it was y equals x squared plus 2x, and it's between 0 and 2. Okay, so let's go back. So how would I use the trapezium rule in this example? So I want the integral between 0 and 2 of x squared plus 2x dx, and I know in the back of my mind it's 20 over 3. And 20 over 3, I believe, is 6 2/3, so 6.6 recurring. Okay, so let's think about this. Now, in questions, they'll usually tell you the accuracy they want you to give it at. So let's say there's my curve. Oh, no, it wasn't. Oh, no, it wasn't. It went like that, wasn't it? Because it was going... Oh, it's terrible. Right. Okay, I will do this. Like that. I don't know. Don't particularly care. Right, okay. So there's my 2. There's my 0. Okay, so I want to find this area here. Okay, with the Trapezium rule. Well, it's up to you. It depends how accurate you want to be. Let's suppose it asks us to use 4 equally spaced strips. Okay, 4 equally spaced strips. So if I cut it in half, then I cut each of those one in half like that. So that becomes that, and that trapezium. Then let's think about it. How big would the spaces be if there's 4 gaps and it goes from 0 to 2? Well, it'd be a half each, wouldn't they? Half. So this would be a half. This would be 1. This would be 2. Oh, geez, not 2. This would be 3 halves. Okay. And the way I like to do this is I like to set up a table. So I'm going to need the lower bound, so x is 0, all of the stuff in between, so a half, 1, 3 halves, and 2. And then I'll need the f of x values for each one. And because we're doing this numerically, you could give it to certain decimal places. I'm probably going to give the exact value here, just because I can. It's an easy function. So when x is 0, if I substitute 0 back into the original thing, 0 squared plus there's 2 lots of 0 is 0. And I'll do the next easy one. When x is 1, I've got 1 squared plus 2 lots of 1, so that's 3. And when x is 2, I've got 2 squared, which is 4, plus 2 lots of 2, that's 8. And now let's fill in the other ones. When x is a half squared is a quarter, plus 2 lots of a half, which is 1. 1 plus a quarter is 5 quarters. When x is 3 halves, I've got 9 quarters, plus 2 lots of 3 halves is 3, so it's 9 quarters plus 3. 9 quarters plus 3, which is 12 quarters. That's 21 over 4. Okay, so how would I use the trapezium to work this out? Well, we've already discussed h is the gap. So in this case, if there's 4 equal strips, the gap is clearly a half. So the integral of x squared plus 2x dx between 0 and 2 is going to be approximately h, which is a half, over 2 times by the first y value, which is 0, plus the last y value, which is 8, plus 2 lots of the sum of all the things in between. So this stuff. So 5 quarters plus 3 plus 21 quarters. Okay, so let's deal with this. So a half of a half is a quarter. 0 plus 8 is 8. 5 quarters plus 21 quarters is 26 quarters. And if I add 3, which is 19 halves and times by 2, I get 19. And 19 plus 8 is 27. So apparently this is approximately 27 over 4. And 27 over 4 is 6.75. And 6.75 isn't actually that far off from our estimation of 6.66, or 6.6 recurring. And you could probably say, well, okay, that's what I was going to say. How can we make this more accurate? Well, you could make it more accurate if you actually made more strips. Okay, if we'd have made h as a quarter, say, so we'd increase the amount of x values we'd need, we'd create a new table and then we'd figure it out. So this time we need a table from 0, a quarter, a half, 3 quarters, 1, 1 and a quarter, which is 5 quarters, 1 and a half, which is 3 halves, 1 and 3 quarters, which is 7 quarters, and 2. Then we'd have the corresponding y values down there. It'd be the quarter over 2, which is an eighth, times by the first plus the last times by 2 lots of the sum of the middle, and we could solve that fairly straightforward. The next question they might ask is whether you've overestimated it or underestimated it. And yeah, so in here, how can I tell at a glance whether it's an overestimate? Jeez. How can I tell at a glance whether, and by the way, this will work with all numerical methods for just in general really. So is it an overestimate or underestimate? I.e., am I going to get a number that's too big or too small? Right, so how can I tell that? Well, the trick is, if I was to zoom in on the function, it all depends if in the area of the function it looks like this or it looks like this, right? Because let's say I zoomed in and the limit was going to there and the limit was going to there. Can we all agree that if I find the area of that bit that I have underestimated? This is an underestimate right here. And similarly, if the limit was coming from the bottom like that, and I moved like that, and then I draw a line between the two, then this is going to be an overestimate. This is an overestimate, because I clearly want the area above the graph, below the graph. You know, I want this stuff, and I overshot it. This is an overestimate. And similarly to the left-hand side, I wanted all of this stuff, but I only got the rectangle, so that was an underestimate. Okay, so what facts do we know about this kind of stuff? Well, when we're dealing with this n-shaped type thing, then we know that the second derivative, d2y by dx squared, is actually negative. Okay, we discussed this last time in calculus, because the gradient is going from a positive to a 0 to a negative. Okay, we discussed this. And then similarly, when it's an overestimate, it's when the second derivative is positive. We're going from a negative gradient to a 0 to a positive gradient. And by the way, the fancy names for these things is this is a concave function and this is a convex function. Okay, so you can just say that it would be an underestimate because it's a concave function. It would be an overestimate because it's a convex function. If you want to memorize it, the N shape, if you think about it on the ground and shade it black, it kind of looks like a cave, and convex is the other one. I mean, you can memorize it how you want to, but concave downwards and convex upwards is generally how people would describe it. So there you go, using the second derivative to help with stuff like that. Okay, so using the trapezium rule is pretty easy. You're not expected to memorize it. You're given it in the formula sheet, but just please be aware of how to use it. There's another numerical approximation I want you to have a look at because it's quite interesting. And now, let's say I've got the following. Right, now this, what I'm about to explain now, is Simpson's rule, like, you know, the Simpsons, spelt the same way. Nothing to do with the Simpsons that we know on TV, but probably more important. So let's say I've still got the same curve, but now I've got the following. Okay, now this is going to be quite difficult, so bear with me. Let's say I still want this area between A and B of the following. I still want that area. Okay, now what I'm going to do, okay, there's a caveat here. What I'm going to do is I'm going to go up. I'm going to go up another 2 spaces. There you go. Like that. And like that. Okay. Now, why is it I've done this? Well, let's call this point here again y0, because that's the first y value. Let's call this bit y1, and let's call this bit y2. And again, these are equally spaced, and let's say they're h along. And you're probably thinking, okay, so what's going on here? Well, what I want you to imagine is I want you to imagine a quadratic. I want you to imagine a quadratic. So we've got to imagine a quadratic that goes through y0, y1 and y2, and that is the thing that we're going to be finding the area under. Now, if it's just in the region between y0 and y2, then in this case that's a pretty good estimator, isn't it? And if you squeeze h together and make that smaller, then essentially you could pick 3 points that are even closer, so like 1, 2, 3, and then that would be a parabola looking like that, and it would look better and better. The point is the same argument applies. This becomes more and more accurate the smaller h's and the more strips you split this up into. So okay, let's try and deal with that. So let's talk about this blue function. Let's call this function g of x. Okay, so let's say f of x is here. So I'm claiming that f of x, let's say this is between x0 and x2, and this is x1 here. Okay, so when you plug in x0, it gives you y0. When you plug in x1, it gives you y1, and so on and so on. So I'm saying that if you integrate x0, up to x2 dx of f of x, this is quite close to if you integrated this x0 up to x2 of g of x dx, where g of x is this quadratic that best matches the curve. Okay, so I don't know what the curve is, but by doing this I can actually force it to be a quadratic. Okay, so what on earth does that mean? Well, what do I know about quadratics? Well, I know that quadratics, let's say my g of x, that is going to be some constant a of x squared plus b of x plus c. Okay, and now what happens? If I was to integrate that g of x dx, this will become ax cubed over 3 plus bx squared over 2 plus cx plus, and let's call the new constant of integration k. Right, okay, so here's the deal. Let's suppose, what can we say? Well, I know 3 bits about my curve. I know that when I sub in gx of 0, I get a lots of x0 squared plus b lots of x0 plus c, and that equals y0. And then similarly, if I sub in g of x of 1, I get a x of 1 squared plus b x of 1 plus c equals to y1. And if I sub in x of 2 into there, I get a x of 2 squared plus b x of 2 plus c, and that equals to y2. Hi, sorry about that. I leant on my keyboard and stopped the recording. I must have pressed the space bar. Right, so where were we? Yes, okay, so I've got this. Right, so here's the thing. We've got a set of simultaneous equations to solve for this, but in actual fact, we can do something incredibly sneaky. And what I'll do is I'll do the sketch over here. This comes down to just areas, right? So the question is, okay, let me draw 2 plots. Let's say that this is the quadratic I've got, and I want the area between here and here. And let's say that these 2 points are 1, 3, and 2 is in the middle, where it's that point there. Okay, now this area, do you agree, will be exactly the same as if I take this function and I just move the coordinate axis, so now it's like that. And so that middle thing is on the y-axis. And the reason we do that is that it makes all of this a lot easier to solve. So we're going to translate this. So what we have to consider is this just gets translated. This just gets moved to the left. And the reason for that is because now, if we treat x1 as our new 0, then this becomes x1, which is 0. And then what happens is all of these disappear, and we're left with the c component of it, which we now know is y1. Now, what else do we know? Well, we know, that h naught now is going to be negative h, because we're going back a h. And we know x2 is going to be positive h. So what does this all become? Well, h minus h squared, minus h squared is going to be just h squared. X naught, that's just a h. On the bottom, minus h squared is going to be positive h squared. And x2, that's going to be negative h. And now, this is what's great about it. We can actually figure out what A and B are. Well, we already know that C is y1. And, well, if you think about it, if you add this line and this line together, then you're going to have two lots of AH squared. The BH's cancel. The two C's are added together, which is two lots of y1. And this is going to equal y0 plus y2. So in actual fact, you're going to get A is y0 plus y2 minus two lots of y1 all over 2h squared, and that equals to A. Okay. Now, funnily enough, actually, that's, that's all we needed to do. And you're probably thinking, okay, why is that? Well, let's think about it. If I wanted to integrate my function, which, by the way, is up here, then if I want to integrate that between minus h and h, then this plus k is just silliness. We don't need it. It disappears. It's like the constant of integration. And we have to evaluate this thing between minus h and h. And now, let's think about what happens. You're going to get, when you sub h in, you're going to have a lots of h cubed over 3 minus plus b lots of h squared over 2 plus ch. And on the right hand side, you can have, when x is minus h, you can have minus a h cubed over 3. And then you're going to have plus b h squared over 2. And then you're going to have minus ch. And what's going to happen, you can have bh squared minus a bh squared. And then these minuses in front, you can take them out as a plus. So actually the area is 2ah cubed over 3 plus 2ch. And now I know what a and c are, so I can sub them back in. So actually let's factorize a little bit. So if I take h out, this is h. And if I take the third out, you'll see why in a second, because it's links to the formula. Then h over 3, that is 2ah squared plus, and then this is going to be 6c. Yep. So h over 3 times by, what is 2ah squared? Well, a is this thing here. And look, I've got 2h squared on the bottom. I'm timesing it by 2h squared, so they're going to cancel. So that's y0 plus y2 minus 2 lots of y1, and then plus 6 lots of c. Well, I know what c is, that's y1, so that's a y1 there. And if I tidy this up, this is h3 times by y0. And then think about it, I've got minus 2y1 plus 6y1, so it's going to be plus 4y1, and then I've got the y2 there. Aha. Brilliant. Now, here's the great thing. This little rule here, gives me the area of this bit here, these two strips that I've made from approximating with a parabola. But now think about it. I could carry this rule on because I know how to shift parabolas left and right. So according to this thing, I could just shift the next parabola on. Well, will the next parabola be on? So let's say I create another pair of equal width strips here and here. And this time it starts at y2, and the middle one's y3, and the next one's y4, and we're h along, and now I'm talking about this area. Okay, and what I'm trying to integrate with that area is I'm trying to imagine the quadratic that goes like that. There's an n-shaped parabola that goes through those 3 points. So I don't know, call this h of x, it doesn't matter. The point is I can keep adding pairs of strips to form parabolas and then integrate under there with parabolas. So can you guess what that would be? Well, for the next region, it would be h over 3, but now this time the first value is y2. I'm going to have 4 lots of the next one, which is y3, and then I'm just going to have a single lots of y4. And then, can you see what's going to happen? Well, I can actually say this integral is approximately h over 3 lots of, and now the first one is y0 plus 4y1 plus y2, plus the next one would be y2 plus 4y3 plus y4, plus, and the next parabola would be a y4 plus 4y5 plus y6, plus, and so on and so on. And then the last one, the last parabola, well, what would that be? Well, the key point is that this only works for an even amount of strips. So to force that, we're going to say we have 2n strips. So that means the very last y value is y of 2n. Why is that? Because y0 is where the first backbone is. y1 gives us the first strip, so that's this bit. y2 gives the second, and so on. So it makes sense that if we've got even amount of strips, the last one must be 2 times a number, which to force it to make it even when that number is an integer. So what would the last one be? The last one would be, well, we know the end would be y is 2n. We know there'd be 4 lots of the one before that, which is 2n minus 1. And there'd just be a single lot of the one before, which is 2n minus 2. Now, we're nearly there. We're so nearly there. Okay. So, this integral can be approximated by h over 3. And then, well, let's have a think about this. There's a y2 here, but there's also a y2 there. There's a y4 there, and there's a y4 there. There's a y6 there, and there'll be a y6 over there. Can you see that when there's odd y's, so y1s, y3s, y5s, there's going to be 4 of them. And when there's even y's, like y2 and y4, there's going to be 2 of them. So when I do y0 plus y of 2n, so first plus the last, and then I'm going to have 4 lots of y and then the odd numbers, and then plus 2 lots of y, and then this is going to be the even subscripts. Okay, and if you wanted to, I'm going to put a little sum like that. So it's the sum of the odd and sum of the even. If you want to be more formal about it, we'll do it another time. But I guess if you wanted to, you could leave it as 4 lots of y1 plus y3 plus dot 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 dot, and the last one you'll have a 4 of is y of 2n minus 1, and then plus you'll have 2 lots of y2 plus y4 plus dot 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 dot, and the last one will be y of 2n minus 2. Be the last even number that isn't y equals 2 of n. And now this super duper thing is Simpson's rule. Okay, now it's really easy to compute, and in fact we're going to use our previous example to show how we did it. So where is it? So up here. Now we took 4 strips last time. Here's our 4 strips. So that is an even amount of strips. So actually we can just take that data and we can try it ourselves. So suppose we wanted to integrate again. We wanted to integrate between, what was it, 0 and 2 of x squared plus 2x dx using 4 strips. And this time we want to use Simpson's rule. So let's remind ourselves what's going on here. So this is going to be approximately h. Well, h is the step we're going up in, and because it's going from 0 to a half in the x and half to 1, 1 to 3 halves and 1 to 2, that width of x is a half. So it's going to be half divided by 3, because it's h over 3. And then it's the first y value, which is 0, plus the last y value, which is 8, plus 4 lots of the odd y value. And now think about this very carefully. This is y0, this is y1, this is y2, this is y3, this is y4. So the odd y values are going to be 5 quarters and 21 quarters. So this is going to be 5 quarters plus 21 quarters. Let's make that black. And then it's plus 2 lots of all the even ones that weren't the first and the last. That's just going to be 3 at the end. Okay, so let's deal with this. So a half divided by 3 is 1/6. 0 plus 8 is 8, plus 5 over 4 plus 21 over 4 is 26 over 4, and if I times up by 4, that's just 26, plus 2 times 3 is 6. Well, 26 plus 6 is 32, plus 8 is 40, so 1/6 times by 40 is 40 over 6, which is 20 over 3. Oh wow, that is exactly 6.6 recurring. So no surprise there, really, if you think about it. We have used a quadratic to approximate a quadratic function. And in this case, it's actually given the exact value. So no surprise there, really, because we're using a quadratic to estimate a quadratic. So what it's doing is it's drawing a quadratic that goes through all the 3 points as it goes along. And clearly, that's going to be the exact answer. So yeah. Trapezium rule is just where we make trapeziums out of it. Simpson's rule is where we make strips of 2 and we find the areas under each of those parabolas between the 3 points and we sum them up. The formulas are here in light green, there and down here for Simpson's rule. Please be aware, I don't think Simpson's rule is in the formula booklet. You need to memorize it. If it is in the formula booklet, you're lucky. Personally, it's one of those ones you just kind of remember. It's first plus last, and then 4 lots of the odd plus 2 lots of the even ones. Hopefully after seeing this, you can probably derive it for yourself, actually. Anyway, so let's crack on. So again, pause the video, give it a go yourself. You can solve this. Be my guest. Okay, so use the trapezium rule with 5 equally spaced strips to find an estimate for I. Okay, well, let's think about it. If there's 5 equally spaced strips, that means, well, I don't have to draw what this is. It means it starts at 1, and there's going to be 1 strip, 2 strip, 3 strip, 4 strips, 5 strips. So really, If the last one is 3, what do the gaps go up in? Well, 1, 2, 3. Okay, so let's think about this. Well, I need to count 2 divided by 5 because there's a difference of 2 between 1 and 3, and there's 5 numbers, 5 strips. So that is going to be 0.4, is it? So 1.4 plus another 0.4 is 1.8, add another 1.4 is 2.2, add another 2.4, 0.4 is 2.6. Yes, okay, that works, that's fine. And now I need my whatever the root x minus log base 10 of x is. And I'm going to do this to 2 or 3 decimal places. You can find the log base 10 button because log base 10 of x is just the log button. So you just type square root minus log, and don't do any of the funny bases, and then the same thing. So what I suggest you do is you use the answer button, ANS. You type out the x value, and then use the up and down arrows to navigate between the two things. So you can probably do this actually quite easily because when x is 1, root 1 is 1, minus log base 10 of 1, or log of any base of 1 is 0, so this is 1. Square root 1.4 minus log of 1.4 to 3 decimal places is 1.037. If I do the same for 1.8 to 3 decimal places is 1.086. If I do this for 2.2, this is a rare case where I'm going to use a calculator. This is 1.140. What's the next one? 2.6. Then this is going to be 1.1974, so it's 1.197. And then when I do it for 3, then to 3 decimal places I get 1.255. This is 1.2549, so the 9 will round up. Okay, so for the trapezium rule, you're given it, but it's going to be h over 2. So it's 0.4, so this is approximately the trapezium I, the integral, we're seeing I there, that is going to be approximately equal to h over 2, so 0.4 over 2 is 0.2, times by the first value, which is 1, plus the last value, which is 1.255, plus 2 lots of all the ones in the middle, which is 1.037 plus 1.086 plus 1.197. Close brackets, close brackets. That is just a calculator job, so 0.2 brackets 1 plus 1.255 plus 2 brackets 1.037 plus 1.086 plus 0 plus 1.197, close brackets, close brackets. That apparently is 2.235 units squared. Okay, that's a good approximation. Yeah, that's pretty much it. The trick with these questions is to build up a table of what you're doing and memorizing what the formula are. Okay, so what's the next one? Use Simpson's rule with 5 ordinates or 4 strips to find an approximation of that. Okay, same deal. Okay, so x goes to 1, and I have 1 strip, 2 strip, 3 strip, 4 strip. So my table is going to look like this. Where I'll call this f of x, and this last one's 3. So it looks like that's going to be 2, that's going to be 1.5, and this is going to be 2.5, and h appears to be 0.5. Okay, so what happens when x is 1? Well, let's give it to 4 sig fig. So what's 1 over the square root of 1, the square root of 1 plus 1 cubed. That is root 2 over 2 as a decimal. I will take that as 0.7071. When I replace x with 1.5, then that becomes 0.4781. When x is 2, I get exactly 1/3, which is going to be 0.3 recurring. 2.5. That is, what, 4 decimal places, 0.2453. And then when I do 3, that's root 7 over 14, oops, daisy, which is 0.1890. Okay. So, what was Simpson's rule again? Simpson's rule was that this approximates to h over 3 times by the first y value plus the last y value plus 4 lots of all the odds plus 2 lots of all the evens. Okay, so remind ourselves that this is y0, this is y1, this is y2, this is y3, this is y4. Okay. So this is going to be h, which is 0.5 over 3. So half third, that's going to be a sixth. Lots of y0 is 0.7071 plus the last y value is 0.1840 plus 4 lots of the odd ones, which is going to be 0.4781 plus 0.2453 plus 2 lots of the even ones, which is going to be 0.3 recurring. So 0.333. And then that's just a calculator job, and we'll bash it in. So 1 over 6 times by 0.7071 plus 1840 plus 4 brackets 0.4781 plus 0.2453 close brackets plus 2 brackets 0.12343 close brackets. That will give us the 3 significant figures, 0.742 units squared. Okay, I believe that's it. Cool, that's all I wanted to go through. There's plenty to sink your teeth into there. By the way, there is so much more to integration than this. At the moment, if you can integrate polynomials and you can use Trapezium Rule and Simpson's Rule to get a numerical value of integrals, that's great. By the way, if you just wanted a numerical value of what the area is under a curve, Simpson's rule and the Trapezium rule work for any integrals. So you know when I said previously we don't know how to integrate sine x, cos x, ln of x, e to the x, funny weird fractional functions like 1 over 1 plus x squared. Well, with Simpson's rule and Trapezium rule we can. I mean, they're numerical estimates and we've seen how they're funny functions. This one's not a polynomial. And then similarly, this function's not a polynomial. Oh, I didn't square the thing. Oh, you silly boy. Okay, so I actually haven't done this one correctly because I forgot to see the squared thing. So really, this has to be squared, that squared, that squared, that squared, that squared. So squared, 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 squared. Oh dear. Right, so let's do that quickly. So if I go back up, 0.2, okay, so I can actually just bang these in, can I? So that's squared, squared, 186 squared, 073 squared. Oh, I can't believe I forgot the squared. That's just silly. Squared and 1 squared is just 1. Oh dear, where did that go? So that will be 2.5098. So that's change that a little bit. So that should have been 2.510 to 3 decimal places. So yeah, my bad. I forgot the squared. I honestly forgot the squared here. In actual fact, let's have a look, see I haven't done anything wrong here. No. Square root 1 over 1 plus x cubed. No, that's fine. Okay, yeah. Apologies for the mistakes. I'm recording these quite late. And yeah, nope. Hope you enjoyed it. And yeah, great work.